from layatforsci.com/MCAT, and in this video, we're going to look at the stereochemistry of amino acids from RNS to D and L. Amino acids are part of biologically active molecules, and just like people are right and left-handed, amino acids are also right and left-handed. Amino acid chirality can be classified as R and S when we're looking at them in a three-dimensional structure, or D and L when we're looking at them in a biological standard format. R and S does not directly relate to D and L. A D amino acid can be R or S. An L amino acid can be R or S. At the end of this video, I'll show you a trick for how to quickly know which is which. In the chirality video series linked below, we talked about how a chiral carbon would have to be sp3 hybridized. That means it's tetrahedral and has a bond angle of 109.5 and attached to 4 unique substituents. To find the chirality, we simply rank the unique substituents from high to low priority, put group number 4 in the back because we're only looking at the 3 highest, and then determine if we go clockwise or counterclockwise when tracing a path from 1 to 2 to 3. The groups are ranked following the Cahn-Ingold-Prelog system, which ranks them from highest priority atom, not group, just the atom attached, to the lower priority. While the periodic table has over 100 atoms, I want you to memorize these 10 because these will show up the most when you're studying organic chemistry. And specifically for amino acids, you're going to see carbon, hydrogen, oxygen, nitrogen, and sulfur. So without memorizing the entire table, recognize that in amino acids, the 5 atoms that we're ranking, sulfur will always be the highest, then oxygen, then nitrogen, carbon, and hydrogen. If you're faced with 2 of the same atom, cross that out and go to the next atom, and then determine again, is it sulfur, which is highest, then oxygen, nitrogen, carbon, hydrogen, until you find a point of differentiation. I know I'm going through this quickly, but that's because I taught it in great detail in the stereochemistry series linked below. Let's try an example. Here I have the line structure version for the alanine zwitterion. Alanine is an amino acid that has the carboxyl and amino group in its backbone. The hydrogen in skeletal structure is invisible, but it's right there in the back, and the R group, which is CH3 for alanine. The first thing we do is identify the chiral carbon, which is the alpha carbon in the backbone, and then rank the substituents. The atoms we're ranking are carbon versus nitrogen versus hydrogen versus carbon. Just in case you haven't memorized it, I'll let you cheat. Sulfur outranks oxygen, which outranks nitrogen, outranks carbon, outranks hydrogen. For alanine, we're comparing nitrogen, carbon, and hydrogen. Nitrogen is priority number 1. Hydrogen is priority number 4. The alpha carboxyl and the methyl group both have a carbon, so how do we know which outranks which? If you remember the trick I taught you, whenever you have a methyl in the presence of a hydrogen, it's automatically going to be priority number 3. Or you can do it the long way and recognize that if the 2 carbon atoms cancel out, the next highest priority on the carboxyl is an oxygen. The next highest priority on methyl is a hydrogen. And since oxygen outranks hydrogen, the carboxyl is priority number 2 and methyl is priority number 3. Group number 4 is in the back, so we cross it out, trace the path from 1 to 2 to 3. And since the top of the arc goes to the right, this is an R amino acid. R and S are enantiomers of each other, and the swap method is when you swap one group to get the enantiomer. This means if I swap the position of the methyl and the hydrogen so that the hydrogen atom is coming forward and the methyl is going back, I expect to have the S version of alanine. Let's prove it. Nitrogen is priority number 1. We've already proven that carboxyl is number 2, methyl is 3, and hydrogen is 4. In this case, hydrogen, which is number 4, is coming forward. So we're going to treat it the same way, but then reverse the direction to compensate for hydrogen not going towards the back. We cross out number 4, trace the path from 1 to 2 to 3, then reverse the direction because group number 4 is forward and we have to flip the molecule. And this gives me the S enantiomer as predicted. You have to know 20 amino acids, but only 19 of them are chiral. The amino acid glycine has hydrogen as its variable group. So if we show a hydrogen that came with a backbone, and then another hydrogen for the variable group, to find the chirality, we rank nitrogen as number 1, the carboxyl as number 2, but which hydrogen atom is number 3 and which is number 4? The answer is neither, because we have 2 of the same substituents. That means we do not have 4 unique groups on carbon, we have 3 unique groups. The molecule is symmetrical, and with symmetry we get achirality. This makes glycine achiral. In organic chemistry, you focus mostly on RNS, but with biological molecules we prefer to put it into a Fischer projection where we can find RNS or the other system D and L. RNS is used to find the absolute configuration because it tells us the absolute order of priority groups. DNL tells us the relative configuration because we see the relative relationship between this amino acid and DNL sugars, specifically the small sugar glyceraldehyde. Fischer projections initially came about as a way to represent a chiral sugar in a simple form. The convention for a Fischer projection is to have a carbonyl on top of the molecule, and the lowest OH group, if it's to the right, tells me I have a D sugar, and if it would be to the left, tells me I have an L sugar. If we want to show amino acids in a Fischer projection, the first thing we want to do is find the OH group. But amino acids don't have an OH group. They do have a carbonyl, which we can put at the top. But what do we use to determine if it's D or L? If we don't have alcohol, we're going to use the amine group, the nitrogen, instead. The convention for amino acid Fischer projections is to use the nitrogen to determine if that amino acid is D or L. If we put the nitrogen to the right, that will give me a D Fischer projection. If we put the nitrogen to the left, that will give me L. Just like sugars, we put the carbonyl on top. I remember this as a tall carbonyl. It needs to stand up, and it stands up at the top. The R group is the variable group. We always draw it on the bottom, so in Fischer projections it's no different. We still draw that at the bottom. And that means the hydrogen is the atom that swaps positions with the amine group in the DNL amino acids. Even though we have potential for 2 types of amino acids, biological molecules will prefer the L form rather than the D form. And the way that I remember this is that our bodies like the L form of the amino acid, and they don't like the D form. Now that we understand the convention, let's turn this molecule, which we already showed is R-alanine, into a Fischer projection. This is where it gets tricky. I'm going to show you how to do it once, but I really don't want you worrying about this because I'm going to show you a trick later to quickly figure out if D or L is R or S, and then you won't need to interconvert this way. Remember that with the Fischer projection, Mr. Organic Chemistry helps us remember that the horizontal bow tie lines are coming forward, and then the vertical spine is going back into the page. There are a couple of ways to put this onto a Fischer projection. I'm going to go with the simplest and then rotate it so it looks like how we want it. If we push that hydrogen up a little so that it's still in the back of the molecule, that will push CH3 into the page as well. That would give me a hydrogen at the top, a CH3 at the bottom, a carbonyl still to the right because that didn't really move, and the amine group to the left. But this is not in the convention that we want. The first thing you want to do is prove to yourself that you converted into the correct Fischer projection, and that means finding RNS. Remember, nitrogen is 1, carbonyl is 2, methyl is 3, hydrogen is 4. Group number 4 is down, just like Mr. Organic Chemistry's spine. We trace a path from 1 to 2 to 3, which gives me R. We know we're correct, but it's not the ideal Fischer projection. To put this into correct form, we can either rotate the molecule or use the swap method that I teach in the chirality series. The R group is in the right place. CH3 is at the bottom. Nitrogen can be right or left for DNL, so that's fine. But hydrogen and carbonyl are in the wrong place. So the first swap we're going to carry out is moving the carbonyl to the top and hydrogen to the right. That's one swap giving me an enantiomer. I need to do a second swap to retain the chirality of the starting molecule. And since I can no longer move the carbonyl and I can't move the methyl, I'll go ahead and swap the hydrogen and the amine. We'll bring the amine group to the right, hydrogen to the left. That gives me two swaps, which is an even number, same chirality as the starting molecule. I'll redraw it with the amine on the right, carbonyl at the top, and hydrogen on the left. Since nitrogen is on the right, everything else is set up the right way. This is a D amino acid. Our alanine is a D amino acid. Are you feeling overwhelmed right now? I would be. On an exam where you need to quickly come up with answers, you definitely don't have this kind of time. So I want to show you something. The second option is the guess and check method. Let's set up our alanine as a random Fischer projection, and then on the Fischer determine if it's R or S. We know the R group has to be on the bottom, so we'll put the CH3 here. The carboxylate must be on top, and I'm randomly going to guess that the NH3 is on the left and the hydrogen is on the right. Let's see if we did this correctly by prioritizing. Nitrogen is 1, carbonyl 2, methyl 3, hydrogen 4. Number 4 has to be on the bottom. If it's not, then if the circle appears R, it's S. If the circle appears S, it's R. We cancel out number 4, trace the path from 1 to 2 to 3, and then reverse it because group number 4 is coming forward, and this gives me S. This tells me I guessed incorrectly, so all I have to do is one swap. Bring the hydrogen to the left, bring the NH3 group to the right, and that would give me the R and therefore D alanine. This is a much faster way, but I have an even faster way that I'll show you at the end. First, let's try 2 more examples. Let's take a look at L-phenylalanine. L tells me the NH3 group is on the left, a hydrogen is on the right, carboxylate is at the top. You should have your amino acid side chains memorized. Phenylalanine is a phenyl group on alanine. Alanine is a CH3, so we make it a CH2. We remove a hydrogen and attach a benzene ring to give me phenylalanine. The 4 atoms we're comparing on this molecule are carbon, nitrogen, hydrogen, and carbon again. Carbon, nitrogen, and hydrogen. Nitrogen is the highest priority, that's number 1. Hydrogen is number 4. And then we have a choice between the carbon in the carboxylate or the carbon in the phenylalanine side chain. The carbonyl carbon has an oxygen. The R group carbon has another carbon as its highest priority. And since oxygen outranks carbon, the carbonyl will be number 2, the side chain will be number 3. We cross out number 4 and trace the path from 1 to 2 to 3, but since group number 4 is coming forward, we have to reverse the direction, and that gives me S. L-phenylalanine is an S amino acid. Now let's take a look at L-cysteine. Once again, for the parent, we have NH3 on the left for an L amino acid, giving me hydrogen on the right, carbonyl at the very top, and the cysteine side chain is a CH2 bound to an SH. For this molecule, we're comparing nitrogen, carbon, hydrogen, and carbon again, same 3 atoms. That means nitrogen is again number 1 and hydrogen number 4. On carbon, we now have to look for the next highest priority. The carbonyl has an oxygen, but the side chain has a sulfur. Sulfur outranks oxygen, making the R group number 2 and the carbonyl number 3. We cancel out group number 4, trace the path from 1 to 2 to 3, and then reverse the direction because number 4 is coming forward, giving me R. L-cysteine is an R amino acid. Now here's the trick. L-cysteine is the only R amino acid All the other L amino acids are S, and I'm going to show you why through logic, and that way you'll never mix it up again. And then if you're given an amino acid in this form, all you have to do is determine R or S, quickly figure out if that's D or L, and then pop it onto a Fischer projection. So how can we know that cysteine is the only L amino acid that will be R? Ask yourself what it takes to get an R or an S amino acid. Every L amino acid has an NH3 group to the left, hydrogen to the right, and a carbonyl at the top. The R group is ultimately going to determine the direction. Nitrogen is always priority number 1, and hydrogen is always priority number 4. Here's the trick for L amino acids. If the carboxylate outranks the R group for an L amino acid, then you're going to get an S chirality. If the R group outranks the carboxylate, then you're going to get an R. If the R outranks, then you get an R. Let's prove it. For the first condition, if the carboxylate outranks the R group, let's make the carboxylate priority number 2 and the R group priority number 3. This means we cancel out 4, trace the path from 1 to 2 to 3, reverse the direction. That is S. That's the first condition. In the second condition, we said the R group outranks the carboxylate, making the R group 2 and the carboxylate 3. Once again, we cancel out number 4, trace the path from 1 to 2 to 3, and reverse the direction, because 4 is forward. That gives me R. That's pretty simple. Here's the fun part. The only amino acid that has an R group outranking the carboxylate is cysteine. Think about what it would take to outrank that carboxylate. The amino acid side chains are limited to some combination of sulfur, oxygen, nitrogen, carbon, and hydrogen. To outrank the nitrogen, you would have to have another nitrogen and then a high priority group on that. None of the side chains start with a nitrogen, so this is locked in at position number 1. The side chains, except for glycine, all start with a carbon. So if we compare what's on the carboxylate carbon to the side chain carbon, we can figure it out. Carbons will cancel out, just like we saw in these last 2 examples. We had a C, and then we went to the phenyl group. We had a C, and we went to the sulfur. The next atom on the carboxylate is an oxygen. The only way for that R group to outrank the carboxylate, it has to have something higher in priority than oxygen. For example, serine is a CH2OH, but the carboxylate has 3 bonds to oxygen. Serine only has 1, carboxylate wins. So if we've ruled out the possibility of nitrogen, if the carboxylate has the most bonds to oxygen, the only way to outrank the carboxylate is with a sulfur. There are 2 amino acids that have sulfur, cysteine and methionine. But if you think about the side chain for methionine, you have a CH2 bound to a CH2, and then finally you have this sulfur bound to a CH3. The C would cancel out compared to the carboxylate, but then the oxygen on the carboxylate will be compared to a carbon. You never get a chance to go as far as the sulfur, and so that doesn't count. But cysteine, as you saw in the last example, has a carbon directly bound to sulfur. This means it's the only R group that outranks the carboxylate. And so instead of seeing the rule as the R group outranking carboxylate is R, just think of it as the cysteine R group outranks the carboxylate and therefore is the only L amino acid with R stereochemistry. Say you're given a structure like this, you're asked to figure out its chirality and to show it on the appropriate amino acid Fischer projection. First, we have to identify what's going on. The amino acid has an alpha carbon attached to an alpha amine and alpha carbonyl, and a 2-carbon side chain with a carboxylate. This right here is our side chain. You should recognize this as the conjugate base of the shorter acidic amino acid, making it aspartate. The alpha carbon is the chiral carbon, so let's figure out if it's R or S. The amine is number 1, the invisible hydrogen is number 4, so we'll just put a 4 instead of hydrogen. The backbone carbonyl is always number 2, except for cysteine, and the side chain will be priority number 3. How do we know? Carbon versus carbon. The carbon on the side chain has another carbon. The carbon in the backbone has an oxygen. Group number 4 is in the back, so we cross it out. Trace an arc from 1 to 2 to 3, and we get S. S-aspartate. Does that mean it's going to be an L or D amino acid? Let's go back to the trick. L amino acids are S unless they are cysteine. We're just reading this backwards. So if we have an S-aspartate, we instantly know that it's an L amino acid, and we draw it accordingly. The amine group on the L gets drawn to the left, the hydrogen is to the right, carbonyl at the top, and the side chain, which is CH2 and another carboxylate, goes on the bottom. Let's prove that we did it correctly. Never memorize a trick unless you can prove to yourself that it's correct. Nitrogen is number 1, carboxylate is 2, hydrogen is 4, CH2 is 3. Group number 4 is forward, so we cancel it out, trace an arc from 1 to 2 to 3, and then reverse the direction since 4 was forward. This is S, and because the NH3 is on the left, it's an L amino acid. Be sure to join me in the next video where we look at how to find the charge for amino acids and zwitterions to justify why I keep drawing them as a carboxylate and NH3+ instead of neutral form. You can find this entire video series along with the amino acid practice quiz and cheat sheet by visiting my website, leahforsci.com/aminoacids.